was like, why is it not up there yet? One last step. Okay, looking at the quiz. For all we know, we have crazy names for things in science. That could mean something. It doesn't, but it's not just obviously wrong. But the two kinds of crust are these two types: the continental crust and the oceanic crust. The lithosphere is a combination of crust plus upper mantle. And so that's not just crust. And so between those, which one is the thicker? Just tell me. The continental is the thicker. It's thicker, it's less dense, floats higher, floats lower as well underneath. What do you call underground seas of water?
Lakes. Aquifers.
Aquifers is correct. Lakes are above ground. Oceans are also above ground. So there would have been a problem if this had been above ground, because you would have had two that you'd be like, I could answer either of those, right? And what about geysers?
I don't like how it's spelled like the...
I'm guessing you looked it up.
Wait, that's actually the wrong spelling.
No, that's the right spelling.
Oh, okay. I thought that was right.
No, that's the right spelling. I have an astronomy video where a guy from Great Britain is talking about geysers, and he's pronouncing them geysers. I'm guessing it's just a regional pronunciation thing. Our region pronounced them geysers like dudes, and they call them geysers like old dudes. So geysers are pockets of water that are heated and spurt up out of the earth. Which type of rock is produced by volcanic eruptions? Igneous.
I was going to do that because both A and C, but I was like, nope. He's tricking me.
Okay, so the three types of rock. We've gone over this. It was on the homework. The homework that I graded yesterday. Igneous rock is when you had molten rock that has frozen. And igneous rock doesn't have to come from volcanoes. It's the one produced by volcanoes, but what's the other way you can get igneous rock that doesn't come from a volcano?
No. No. Like just the lava, just kind of.
Is it just magma cooling?
Magma that cools in the earth instead of. And so that would be things like granite, right? When you have these plutons, these magma chambers that froze underground.
What's metamorphic rock?
Okay, so what's metamorphic rock? Metamorphic rock is any kind of rock, so it could have started out as either sedimentary or igneous. That has been heated, compressed, and possibly chemically changed. And so things like marbles and metamorphic rock, it was limestone or calcite, and it's been heated and squished to transform it. So metamorphic has been metamorphized, it's been changed. Sedimentary is stuff that has settled out and been compressed and lithified. So sedimentary rock is the result of the weathering and erosion processes. And then, of course, erosion is the transport. When it sediments out, then it gets compacted and forms a rock. Final question. What does it mean for a rock to have cleavage?
Breaks along a straight line.
Yes.
This was my first 100%.
I'm glad to hear that it's 100%. Not just your first, but I'm glad you got 100%. So it breaks along a straight line and forms flat planes when you split it. Whereas if it has fracture, that means it shatters when you strike it. Purity is not part of it. I assumed that was a shot at levity there that was still within taste. Any questions about the quiz?
So if you mark on our PTQ, like in the corner, that means you're using that, right?
If I mark it, that means it could show up in a quiz and or test.
Okay, so if it doesn't doesn't show up on a quiz, then they can expect it on the test.
No, it just means it's in the database if it's marked. It's not definitely going to show up. It could. If it doesn't have the mark, then it won't be showing up.
So if it
Unless somebody else asks the same question. If you got a 4 for originality and it's not marked, it still could be on the test because somebody else could have asked the same question. I chose that one. Yeah.
So if it doesn't have a mark, does that mean it's a bad question?
Not necessarily. It just means it's not one that I... All right. Now, before we get started, here's the topics for the day. We're going to finish talking about some water stuff. So we're going to talk about these things down here and then start in with the last thing that's on the homework due Wednesday, talking about the about geology and the geologic time and sedimentation. I have to admit, we had a little bit of a problem. I set my office worker to taking the homework and removing all of the answers and changing the dates. And Hannah informed me actually a week ago that it hadn't been done, but it wasn't until yesterday that she said, no, really, you have the answers here still. And so then I looked and I was like, yes, I do. And so I fixed them last night. Hopefully that wasn't an impediment to you because like you have the answers, it takes away your ability to really think about it and figure out the answer. Right, so that's to your disadvantage, and I apologize for that. Okay, before I get started, I did promise I was going to show you this video about continental drift just from YouTube. What are the chances I can make it go full screen without everything failing? So far, so good, right? Okay, so there is sound that's unnecessary here. Notice the names in the bottom right-hand corner. Actually,
Are you about the names that are behind you?
it's interesting. That's as soft as I can make it. Well, I can do this. Now there's no sound.
If there's no sound on that, does that mean there's going to be no sound on the...
There will only be the sound of us talking.
Okay.
So the supercontinents is when you have things come together. And so you notice it started with just a little thing and then it's moved around. Right now we have no supercontinent, right? There's no big clump. Notice the time. 2,260 odd MYR. That means million years ago. And so this is going way back in time. And the first thing that should come to anyone's mind is how did they get this? It's a combination of a few things. They look at the fossil record. They use dating techniques. That is, we've already learned about radioactive dating. They use that to determine the age. They look at magnetic field orientations. They look at the types of sediment. You know, some would be oceanic or you have, ones in water, ones that are not in water to try to get all the information to put together to form these. So here we have a supercontinent, Columbia. You look at that and you might think that you recognize some pieces, but then over time as they change, you kind of lose confidence. So most people have heard of Pangea. Not Pangea, right? There's different supercontinents, and you'll see lots of them down there in the bottom right-hand corner as we go through time.
Convection currents?
Convection currents from the mantle. That's right. So now it's broken apart. No more Columbia. I don't remember the date for Pangea, so I don't remember if we're past it or not. The one that everybody knows. Things are coming together. Rodinia. by the way. You can look and see the color codes. Things that are North America are, I believe, this color. Things that are Africa are this color. The white is Antarctica. Pannotia. Gondwana. Now, since we're going to be talking about time, the estimated time for the Cambrian explosion, when we had a sudden proliferation of lots of different species, is around, I think it's 540 million years ago. So this now is after the first fossil layers that tell us, about old animals. Keep in mind, this is the dating given by scientists using radiometric dating. There are many people who are going to dispute those dates, and I'm sure there are people in this class who are going to dispute those dates, and I'm fine with that. Right? The scientific explanation is this many years. I used to have a very firm belief in it because it's based on radiometric dating, something that we can test pretty well. But now I have more questions, more doubts, because of them finding soft tissue in dinosaurs, soft tissue things like proteins, that they should be way too old to have any soft tissue. Which makes me wonder if the dating really is flawed and we don't understand. We have some basic physics problems. Grace.
It's not very accurate when you get like that far away, too.
It depends on what you mean by accurate. It's going to be less than 10% error. So if you're talking, 414 million years ago, you're not going to be off by more than, let's say, 40 million years. 40 million years is a really big amount, but it's still not going to make a big change because percentage-wise, it's not a big one. Okay, so let's keep going from Gondwana. Now you can start to see things coming together. You can see North and South America with Africa right next to it here. So now you can recognize Pangea, the one that everybody's heard of, or most everyone's heard of. And of course, we know Africa has to break away here. And so there it goes. Look, Africa breaks in parts and then it'll come back together. And look at India. India is often called a subcontinent. I just love the way it flies north and slams into Europe or Asia. Okay, so that is an animation of our best understanding of how plate tectonics has really reshaped the Earth over time. Now, once again, going to what Bryson had asked about, how does a young Earth creationist explain this? And what was the answer, Bryson?
Well, a young Earth creationist, didn't you say their answer is the flood?
Their answer is the flood. Because, we believe from the flood story, right? If you believe the flood story, which I do, then you believe that the Earth was broken apart at the time of the flood.
And that's what caused the different plates.
Yeah, so you would have then the motion beginning, the plates moving, and where plates collide, mountains being built, and so on. And so it works with the scientific data with one exception, and that's the dating issue. There's also the fossil record that is explainable kind of, well, some people will take it as a strong, some will not. The fossil record, which shows a general trend of less sophisticated things down lower, more sophisticated things up higher. that is explained or interpreted. We're going to say something.
Yeah, I'll let you finish though.
Feel almost like Kanye West here. That is explained by a zonation thing, talking about this is where these things live, this is where these things live. In the time of flood, everybody's running for higher ground. The ones that are bigger, have longer legs, are going to be more able to get to the higher ground, and so they're going to be found at a higher level. And so that's an explanation given to try to explain the fossil record. Whereas the scientific, well, we'll talk about the scientific explanation in class today. So, I said, okay. Well, I could have let you talk because it's always better when it comes from students and they're expressing their thoughts and clarifying their thoughts. So you should have just said, no, yeah, I got something to say. Okay, now, a few more things on water. What do we see in this picture? What features stand out to you?
Rapids.
No, I'm not going to have rapids in this picture.
Snake Lake.
Snake Lake. I've never heard that term.
Turbulent flow. Yeah.
No, not turbulent.
Delta. Is there nothing? No.
Not a delta. We've ruled out all the things that are wrong. Okay. Let's look in this picture. Okay, so you talked about the ox. Here's an oxbow lake right there. Right, this stream, you can see it used to go like this. And rushing water cut that off, but then it's moved over. And so we call this kind of feature, the shape of the stream, a meander. Because it meanders back and forth through a region. And that region that it meanders back and forth through is called a floodplain. So that's why the correct answer here is a floodplain. That's not a term that I talked about in the preceding class. So when I asked what you're seeing here, I was looking for what you're seeing and not necessarily what's the correct answer. So we see a meander going through a floodplain. So that floodplain, its boundaries are going to be something like, oh, come on, really? Boy. Over here, it looks like it's more, well, just going like that. Right? That whole thing is a floodplain. When I think of floodplain, I think of, right now, if you drive to Omaha, when you go across the Platte River, you see that what we usually think of as the flat of the Platte River is not the entire floodplain. There's a huge floodplain there. So a couple Sabbaths ago, we went out there just to observe it, and my wife was like, why do they have farms there? Well, you see here they have lots of farms in the floodplain too. Why do they have farms there in the floodplain? It's fertile soil. It's good for growing.
And also it's easy to irrigate the river right there.
Easy to irrigate? I'm guessing this comes from family conversations and experience. So it's a good place to grow stuff. But it's also a place that you have to recognize will be periodically flooded. You know, how often? If you're lucky, it's once in 100 years and your farm is never affected. If you're unlucky, it's once every 10 years, which it seems is more reasonable for floodplains on the Missouri River. And so if it was me, I would try to keep my farm buildings outside of the floodplain and just have my actual agricultural land in the floodplain. But there's a cost to that because of transportation. Right? If you're transporting your tractors 10 miles every day, that's going to cost you.
Couldn't it flood your crops too?
It does. You're going to lose your crops. So this year we're going to have a dramatic decrease in income for farmers in the state. There should be federal money to help offset that because we absolutely need the farmers in the Midwest. And if you just let them all go bankrupt, what happens next year? Yeah. All right. So here's a picture showing a typical floodplain. What created this floodplain? The stream coming back and forth. When it gets to the edge, it erodes a little more, and so it digs it out a little. And so here you have the floodplain. You see this soil here looks different than the other soil because that's all sediment. The river has worn through and then dropped sediment. if you have rapid turbulent flow, then you're going to pick up material, and that's when you dig deeper. And then when it slows down, you drop out material, and that's when you build back up the sediment. And so that sediment everywhere is what actually makes for the fertile soil. And its locality, its location, the fact that you have water very nearby is going to make it easy for irrigation. Now, one of the homework questions, I think it's one that's due to on Wednesday, has to do with the word delta. Delta is a Greek letter. Here's a capital Greek delta. Now, most of us, without having any knowledge of Greek, look at that, and what do you say? Triangle. And then you start singing They Might Be Giants, right? Triangle man, do things triangle can. No?
No.
It's a shame. That's what I do. So that's a delta means a triangle shape when we're talking about it in terms of geology. So delta is where you have flowing stream meets a standing body of water. What's an example of this? Well, here's a really famous one, the Nile Delta. Does anybody know what the Nile Delta is? I mean, obviously, it's got to be a delta.
The delta of the Nile River.
Okay, we're really good at parsing English here.
Isn't that when the river flows into the ocean?
Right. That's where the Nile River flows into whatever that ocean is.
Can I tell you a quick story?
You can regale us.
So, I heard a story about a ship that wrecked off the coast of South America in the Delta, and they were stranded, I don't remember how long, I think it was like a week, and they didn't have very much fresh water. And then they learned after they got rescued they couldn't drink the water because the fresh water flowing out goes miles out into the sea.
Now, the water there would actually be considered brackish. Brackish is a combination of the salt water and the fresh water. So it's not going to be the full salinity of the sea, but it's going to have some salinity. So it probably was drinkable is the key. And if they could have got out of the ship and just gone upstream, then it would have been pretty pure. So what creates a delta? It's a location where a river runs into a standing body of water. So the Nile Delta, the Nile River, runs into a standing body of water. Down in Louisiana, there's a delta where, what's the river there? Is that the Missouri? Yeah. Flows into the Gulf of Mexico. And so you have all of the sediment load that the stream has been carrying down, which right about now is going to be a whole lot of sediment load because of the flooding conditions. It meets the still water and it falls out. And so the ocean starts getting filled up there where the stream meets the ocean. And of course, it's going to fill up most right where the stream meets the ocean, and then less as you go away. And so it's going to form a pattern of filling, such as this picture here is, I believe, okay. I can't remember which one I took this from, which is sad. I think it's actually, no. I'm not going to go out on a limb here and be wrong. My gut says that it's that it's New Orleans, but you have the stream originally, okay, change color. Stream originally met the ocean there, but it's kind of filled in, so the ocean, instead of going like this, is now.
Is that from the sediment?
Yeah, so you have, this is all sediment here. It's still underwater, I believe, in this region I've marked out, but going down, bringing out, and you see a triangle. Obviously, this last side is not a straight triangle, but that's where you get the name delta from.
It's a delta B.
It's a delta B. Good job, Amber. Nailed it. Okay, so back to this. Some other features that you get in the conditions where you have water running into the ocean is you tend to form marshy areas, and you have channels that go through the marshy areas. With out here, you have things like sandbars that will form. sandbars because it drops stuff, builds kind of a barrier. So you have interesting depositional features where you have flowing water meeting standing water, because flowing water is going to carry sediment. Standing water is going to drop out. Finally, for the water chapter is glaciers. Glaciers are defined as regions where you have ice year-round. So here in Nebraska, we don't have ice year-round. We don't have glaciers. But there are plenty of places in this earth where the ice lasts year-round. You have a glacier. And of course, the most common places to have glaciers would be up at the Arctic or Antarctic. We have glaciers that are very old. You don't think about this, but glaciers are ice, and ice flows, just like everything else. Just like we talked about the magma flowing and whatnot. Now, two types of glaciers are alpine glaciers and continental glaciers. Continental are going to be ones that are more flat sheet glaciers. Alpine glaciers, they're in mountains. They're going to flow downhill. So the alpine glaciers are going to be moving, and as they move, if you have ice sliding on ground, what do you expect to happen?
Oh, that
Okay, it's going to make a U-shaped valley.
yeah, U-shaped valley.
I'm looking for something simpler. It's going to drag and grind. It'll grind up rock. It'll drag the sediment with it. And so it's going to cause that U-shaped valley that you brought up. So here's a picture that illustrates, and it's not a very good illustration, the flow of ice over bedrock. So here you have bedrock. What is bedrock? Bedrock is a large, hard rock plane that underlies everywhere in the world. If you dig down far enough, you're always going to hit bedrock. How far you have to dig is going to vary from place to place. And so here we're saying, okay, the glacier's already cleared away any soil, and it's down to bedrock. And so you have the ice flowing in the bedrock. What makes the ice flow? Gravity. Gravity is the prime motivator here. So the gravity is pushing down, and because you have a slope, gravity is going to make it move like that. But the ice, of course, you know ice cubes are pretty hard, pretty stiff. So the ice doesn't flow easily. And where you have the ice touching the ground, that ground is going to try to keep it from sliding. You have friction. And so this is showing some time frame. It doesn't give us a time frame. It doesn't give us distances. But over some time, delta t, the ice slipped this far on the rock. But then the ice deformed, so this line here has moved up here. And of course, other materials moved up as well. So what you have is differential speeds. It's moving fastest the farthest away you get from the bedrock. Slowest the closer you are to the bedrock. The same occurs when you have water going through a pipe. If you have water going through a pipe, the water right next to the edge of the pipe is moving much slower than the water in the center of the pipe. Water is a much more viscous, much easier flowing material than ice. So the difference between the center and edge of a water and a pipe is going to be much bigger than the difference for the ice here. But it's the same principle. So the top is flowing at a different rate. See all these things here? The crevasses, cracks. Why do you have those cracks? Because of what? Okay. Part of it is water melting on the top and flowing, or air blowing over the top as well. But another part is you're creating cracks because of the ice deforming as different parts flow at different speeds. And so even if there were no weathering agents that we normally talk about, you'd still be forming these cracks because of the deformation occurring in the ice. Now, as the ice, here's the life cycle I know there's words on the slides, but we don't care about the words. We care about the pictures. Just like when I was 3. This is showing the life cycle of an alpine glacier. Up in the mountains, it snows. Yay. When it snows, you put down more ice. That ice gets compacted and forms your glacier. If you have more snow, then you have evaporation and this term here, sublimation. Sublimation is going from solid straight to gas. So it's evaporation is going from liquid to gas. Sublimation is going from solid to gas. So if you have more deposition than you have sublimation and evaporation, then your glacier is going to grow up here. Gravity is making it move. Ablation is a general term for removing material. I have my doctorate in laser ablation, in vaporizing materials with a laser.
Wait, what is ablation?
Ablation is removal of material. So where it says ablation dominant, that means you're losing more material than you're gaining. Where it says accumulation dominant, you're gaining more than you're losing. So here you're having the growing glacier, and here you have the shrinking glacier. Shrinking, ing. And so what's going on in most glaciers today? Okay, there's more ablation than there is accumulation. There's accumulation and ablation, but there's more ablation than accumulation. And so they're receding.
I've heard of some people that are scared for the icebergs melting because they might hold pathogens or things that we don't have antibodies for.
It's a possibility.
Yeah.
Dilution is always our friend, and it seems that it would be dilute enough that it probably wouldn't cause a problem, but it's a concern. Just not one that I highly worry about.
I think the water rising is
water
bigger.
Okay, so let's talk about the water rising. And I agree with you, okay? Not saying let's talk about it to disagree. So why would water levels be rising?
Because of the melting of the glacier.
Okay, well, if I have an ice in a cup and the ice melts, what happens to the water level? Okay,
Raise it.
I have ice water, so it has a water level, it has ice floating in it. As the ice melts, what happens to the water level?
Water level actually kind of goes down because the ice takes up more space.
Then water, yeah.
Okay, we have two opposing answers, and the answer is in the middle. What did we learn with Archimedes' principle? The volume displaced is equal, the weight of the volume displaced is equal to the weight of the floating object. Well, that means ice displaces water with the same mass as the ice. And so when it melts, what's the volume of the ice going to become? The same as it was displacing. So when ice that is floating melts, it makes no difference to the water level. And now a person might say, aha, then it's not going to matter. And Richard was disagreeing with Bryson. Not so fast. The Arctic ice is floating. So if the Arctic ice all melts, what happens to sea levels? Nothing. The Antarctic ice is a continental shelf. There's continent, there's rock there that's above sea level. And then there's ice above it. So this is not ice floating in water. When it melts, what happens?
Water level rises.
Water level rises. So there is a concern. It's the Antarctic ice that is the concern, though, not the Arctic ice. Now, you also have glaciers that are on land masses like, Greenland. Greenland glaciers that melt is going to go into the ocean and raise ocean levels. And likewise, any alpine glaciers we're talking about here, or continental glaciers, things that are over land, when they melt, they will raise sea level. While I'm on this topic, I know I'm completely destroying my time schedule, global warming. How do we measure global warming?
Isn't it by the polar caps?
Okay, there's a lot of different techniques used. There's a lot of different techniques. So one technique, for instance, is to look at temperatures in the upper atmosphere.
Is it one way to look at CO2 levels?
Um,
CO2 is being absorbed in the atmosphere.
CO2 levels is one way. If the CO2 levels are higher, then that's indicative of a warmer environment because hot water can't hold as much carbon dioxide as cold water. So if it warms up, CO2 levels rise, regardless of man. That's not used for today because man is producing so much CO2 that it's way overdoing what you would get from measuring the changes in carbon dioxide level. But you're right. For historical climatology, that's one of the proxies they use. They look at the bubbles, measure the content of carbon dioxide, and use that as a way of determining what temperature was. Another way is to have weather stations all over the globe. You measure the temperatures, and then you take an average of temperatures around the globe. And that's the one we usually talk about. That's also the one where you see the most manipulation of the data. Because what happens when you build a city?
Greenhouse gas.
Okay, you put a lot of greenhouse gases, but as the song goes, you also pave paradise and put up a parking lot, right? You take what was green land and you put up a parking lot. Well, that parking lot is going to change the local temperature. You have a bunch of people living, changes the temperature. So you have a heat island effect where people move in and they change the temperature. As the city is growing, its temperature is going to change because of the more people. And so the atmospheric scientists or climatologists try to account for that by saying, okay, this is the actual temperature, but we're going to adjust it by this amount because of the number of people here. And so they're making adjustments to the data to try to compensate for the local effects where their measuring stations are. And so both sides will make arguments about that. But one of the things that I think is really important is looking at the ice we have. Because, of course, heat is required to melt ice. And what happens to the temperature of the ice as it's melting? You put heat in, what happens to the temperature? It melts, and what does the temperature do?
It goes down. I mean, it goes up.
If it's melting, it stays the same. The energy went into converting it, not to changing the temperature. So if the ice is being melted, we're heating. Our temperature isn't changing, but we're heating because we're changing phase. And as long as we have a lot of ice, the Earth will actually buffer the temperatures. As more heat comes in, more ice melts. But there's some other things. Ice helps reflect solar radiation. So the more ice you have, the less heat you absorb. And so as you lose ice, you can absorb more heat. And when the ice is all gone, all of that heat is then going to go into raising temperatures. And so the real concern would be when all the ice is gone, then temperatures are going to start rocketing up. Okay, so that was way off topic, but it's very applicable. I mean, you guys are going to be teaching kids, and it's important to have some knowledge about these things. Did we talk about the greenhouse effect before? Okay, we should talk about that while I'm on the topic. First and foremost, greenhouse effect, good or bad?
Bad. Well, I mean, good if in small amounts because it protects you from UV radiation. But
It's actually the ozone layer that protects us from the UV. The greenhouse effect is vital. Without the greenhouse effect, the Earth would lose way too much heat, the temperatures would plummet, and we'd all be popsicles. So there's no life on Earth without the greenhouse effect. It's necessary. So why do we make a big deal about the greenhouse effect?
because it's too much.
Too much. Too much greenhouse effect means that global temperatures are going to go up because the greenhouse effect, if you've ever been to a greenhouse, you have some good feel for this. You have light that comes through the greenhouse windows. Why does it come through? Because those windows are transparent. But when the light energy is absorbed by the ground gets warmer. And the ground gives off radiation. It gives off the same type of thing, electromagnetic radiation, that's what light is. But it gives it off in a different range. The sun is primarily giving us visible light, whereas the earth is primarily giving off infrared light. That's light with the frequency that's lower than red. And the atmosphere, just like your greenhouse glass or plastic, absorbs the infrared. So it passes transparent or visible light through, but it absorbs the infrared. So it's a one-way gate. Energy can easily come in, but it can't easily escape. And the temperature will then increase until you reach an equilibrium between the energy coming in and the energy going out. So we have to have that greenhouse effect or it's too cold. But if we have too much greenhouse effect, then it gets too hot. And so the greenhouse effect is a very important thing when you talk about global climate, but it's also vital that we have it. If we don't have it, we don't have life. Things that I hope that you could pass on to your students when you're teaching. Okay, one more thing on this. Clearly, I'm not getting to the time part. When a glacier meets the ocean, it will break off in pieces that are it's called calving, like giving birth to a calf. So if you take a cruise to Alaska, they'll take you up to a glacier where you can see it calving, see pieces falling into the ocean, which is totally cool. We take a cruise to Alaska, you're probably also going to hit Juneau. And Juneau, they have this great Mendenhall Glacier that now you have to take a bus a few miles up from the ocean to get to the end of it. Why do you have to take that bus up there? Because it's been retreating, been moving back. A few years back, wow, it's been 8 years now, I went up to Banff and we visited a glacier there. And you can see, in the last 40 years, it's moved a great distance back. And so, the signs of the retreating glaciers is very clear. Of course, if you go back to 1970, the glaciers were advancing. Everybody's worried about global cooling then. Here's two pictures. One very near and dear to my heart. Every summer we would go to Yosemite National Park. You have back there is a feature that hopefully you recognize. Anybody know what I put a box around there?
An alpine glacier.
Sadly, no. There's no active glaciers there. That's Half Dome. It's a big granitic pluton. They often come out shaped in a dome. They exfoliate, which means that pieces will break off and gives it that nice dome shape. And of course, Half Dome has been sheared off on the front. And then you have this one here. Anybody know what this is? It's got a Spanish name. No? No one else is from California, right? That is the captain.
I almost said that too.
El Capitan. When you come through the tunnel into Yosemite Valley, this is the view you have. I always have to stop. It's just so beautiful with El Capitan on the left and straight ahead Half Dome. And if you look further, you have, actually, I think that's from the tunnel view. And there you have a nice waterfall. I believe that's Yosemite Falls, but I would have to look more carefully. I'm not sure on that. But if you look at this, you have a U-shaped valley. That's typical for a glacial valley. The glacier came in, scraped everything clean, so you would have had a rock all the way to the bottom, and then rivers running through, dropped sediment to fill in this nice flat Yosemite Valley. Here's a picture of an active glacier. Now, I have to tell you, the first time I looked at a picture like this, you know what I thought? I thought that they had just paved it and put a road down there. You have with glaciers a bunch of rock that gets torn up. And that rock is called moraine. And I think that's spelled right. That's an N at the end. And so you have edge moraine that's occurring along the edges. But then you have things like this, and you might say, what's causing that moraine? Well, it was edge moraine here, but then another glacier joined in, and so then you have ice between the two moraines. And if you look back further, you have an edge moraine here. This one here was not an edge. There was an edge. There's another one that they come in, they give you these. So those are, it's all moraine.
So moraine is the rocks that glaciers.
It's the ground up rock from the glacier, yes. And all of this is just flowing downhill. Now you have erosional landforms that are cool, things like a hanging valley, a U-shaped valley. Let's look at what you get when you have a retreating glacier. Anyone here from Minnesota? No? Well, Minnesota is the land of 10,000 lakes, right? Why does it have so many lakes? Because it used to be covered by a glacier. And when the glaciers drag a rock, you form these things here, the drumlins. And you have little streams that flow under a glacier that create these eskers. So the eskers are the remnants of a stream or a stream. And then you have the terminal moraine here. What does terminal mean? Okay, stop. It's the end moraine. So as this glacier is moving forward, it is pushing material forward. And of course, moraine was coming down the top and being deposited. And as long as the glacier moves forward, it keeps moving that stuff forward. But when the glacier starts retreating, the stuff stays. And so the terminal moraine is showing you the farthest that the glacier advanced here. And that's all the ground up rock and stuff that the glacier brought forward with it. And now that we're out of glaciers, this will be my last thing. Wind is another erosive agent. It will transport material. And if you have a little sand dune, it will become a bigger sand dune. Because air that's moving will carry more sand. So air moves over this, carries more sand, gets over here, and it slows down. And it drops the sand. And so it'll carry sand up one side and drop it on the other. So that means you're going to build up layers of sand going up this way, making it bigger and bigger and bigger. So that's how big sand dunes occur. And that's how you get layers of sand for sandstone that forms rock. And that's where we stop today. Have a great day.